Every time you ride in a car, shoot a basketball, or even just walk across the room, you're using Newton's laws of motion. These laws are the rules that explain how things move or don't move when forces act on them. And they're not just for scientists. Engineers, doctors, athletes, and even video game designers use them every day. So let's break them down and see how they show up in real life. First, Newton's first law. It says that an object will stay at rest or keep moving in a straight line at constant speed unless a force makes it change. That's inertia. Think of it like this. If you're sitting in a car and the driver slams on the brakes, your body keeps moving forward. That's why you need a seatbelt, to apply a force that stops you. Without it, inertia would send you flying. Same thing when you're carrying groceries in the back seat and you stop suddenly, they slide forward. That's inertia again. In space, this law is even more obvious. There's almost no friction, so once a satellite is moving, it just keeps going. Engineers use this to plan spacecraft paths. They don't need to keep firing engines to stay in motion. In sports, a hockey puck glides across the ice because there's very little friction. It keeps going until something, like a stick or the wall, applies a force to stop it. Now, Newton's second law. This one is the workhorse. It says that force equals mass times acceleration. F equals ma. That means if you want something to accelerate faster, you either push harder or make it lighter. Engineers use this every time they design a car. Want it to go from 0 to 60 faster? You need more engine force or less weight. That's why race cars are built with lightweight materials. It also explains why braking takes longer on icy roads. The tires can't apply as much force because there's less friction. Less force means less deceleration. That's why stopping distances increase. And in a crash, this law explains why airbags and crumple zones matter. If you can increase the time it takes to stop your body, you reduce the acceleration, which reduces the force. That's F equals ma in action. Doctors use this law too. When analyzing injuries, they look at how fast someone stopped and how much force their body experienced. Helmets, pads, and soft landing mats all work by increasing stopping time to reduce force. In robotics, designers use this law to calculate how big a motor needs to be to move a robotic arm. If the arm is heavy and needs to move fast, you need a lot of force. That's F equals ma again. And now Newton's third law. For every action, there's an equal and opposite reaction. You push on the ground pushes back. That's how you walk. Your foot pushes backward, the ground pushes you forward. Same with swimming. You push water backward, and the water pushes you forward. Rockets work the same way. They push gas out the back, and the gas pushes the rocket forward. That's how they move in space, even with no air to push against. This law also explains recoil. Fire a gun, and the bullet goes forward while the gun kicks back. Equal and opposite forces. In sports, when a tennis racket hits a ball, the ball pushes back on the racket. That's why your hand feels the impact. Shoe designers use this law to improve grip. The more force your foot can apply to the ground without slipping, the more the ground can push you forward. Now, in real life, all three laws work together. Take a crash. Newton's first law explains why your body keeps moving forward when the car stops. The second law explains how much force your body feels based on how fast you stop. The third law explains how the wall pushes back on the car with the same force the car hits it. Engineers use all three laws to design safer vehicles. These laws show up in tons of fields. In transportation, they help with braking systems, crash safety, and fuel efficiency. In aerospace, they guide rocket launches and satellite orbits. In medicine, they help analyze injuries and design prosthetics. In sports, they improve technique and reduce injury. In robotics, they control movement and force feedback. And in video games, physics engines use Newton's laws to simulate realistic motion.
Even though we now have Einstein's relativity and quantum mechanics, Newton's laws still matter. They're incredibly accurate for everyday speeds and sizes. They're the foundation of most engineering and science, and they're simple enough to use without supercomputers. That's why they're still taught in every physics class and used in every design lab. So next time you slam on the brakes, jump in the air, or toss a ball, remember, you're not just moving, you're following Newton's laws. And they're not just old science, they're the invisible rules that keep our world running.